All right, so we're looking at 9.5, which has a lot of tests for determining convergence or divergence of series. So let's just jump right in. One of the ones we've already talked about is the ratio test, and remember, it's useful. It's very useful. I use it a lot. But if we're talking about the series of a sub n, and if it's a series with positive terms, and the limit as n approaches infinity of a sub n plus 1 over a sub n equals L, in other words, it equals some numerical limit, doesn't matter what it is, as long as it's actually a number, not infinity, then the series will converge if that L is less than 1. It will diverge if that L is greater than 1. So the ratio of one term to the, one term to the one previous to it, the limit as n approaches infinity. If that approaches a number that's less than 1, then it's going to, the series will converge. If it's larger than 1, it's going to diverge. Now remember, it says here with positive terms, but you can also go in here and put in absolute values around your a sub n plus 1 over a sub n. Now if it equals exactly 1, then we call the test inconclusive. What that boils down to is try another test, because that's not giving you any information on whether it's divergent or convergent. So you got to try another test. All right, this section of the book presents several other tests or techniques used to test for convergence and discusses some specific convergent and divergent series. Now, I've also given you your sheet of tests that tells you or gives you pretty much all the tests that you're going to be responsible for. Matter of fact, some of those you're not even going to use, but they are all very good tests to remember. If you focus on your P series, knowing about your geometric series, the ratio test, and comparison tests, you're going to be in pretty good shape. But there are some other ones that are nice to know. The integral test we'll talk about, but those are the primary ones that you want to focus on. All right. Also, we have the nth root test, which says if sigma a sub n is a series with positive terms again, and the limit as n approaches infinity of the nth root of a sub n equals L, then the series will converge if L is less than 1. The series will diverge if L is greater than 1, and it's inconclusive if L equals 1. A lot of the situations that we're dealing with, this is going to be what's happening. So different tests, but same conclusions, and same conclusions for the same values. So the reason this is called the nth root test, notice we take the nth root of a sub n, and then we take the limit as n approaches infinity. All right, so let's look at an example here. We have the sigma notation n equals 1 to infinity of n squared over 2 to the n. We're going to do the nth root test for this. So we take the nth root of a sub n, here's our a sub n, and notice on the bottom when we split this thing up, let me write an intermediate step in here for you. This will be the nth root of n squared over the nth root of 2 to the n, and that's why these cancel out to give you the 2 right here. So that's where this one comes from. So the nth root of n squared over the nth root of 2 to the n, which simplifies down to 2. Now, remember, when we're taking a limit of this thing, remember we're taking the limit as n approaches infinity of the nth root of n squared over 2. Well, this 2 on the bottom is not going to be affected by the limit. So we can actually pull this all the way out to the front and think of that as 1/2 the limit as n approaches infinity of the nth root of n squared. That makes it easier to deal with our limit. So we can deal only with this part and then come back and multiply that by 1/2 to find out what the limit actually is. So the limit as n approaches infinity of the nth root of n squared is the same thing as the limit of n to the nth root of n quantity squared. Is that true? Well, it actually is, and we can deal with just the n approaches infinity of the nth root of n, which is n to the 1 over n power. Then once we find the results of this limit, we can square it. All right, so of course with the crazy power here, we're going to have to do some natural log and exponential things. So we get the exponentiation out. And we've got e to the limit as n approaches infinity of the natural log of n to the 1 over n. And we can bring that 1 over n out front. So we've got e to the limit as n approaches infinity of 1 over n times the natural log of n, or the limit as n approaches infinity of natural log of n divided by n. That's the same thing. And when we take that limit, what's going to happen? Well, if we let this go to infinity, that's going to go to infinity, and that's going to go to infinity. So L'Hopital's rule comes in because we got infinity over infinity. And when we do that, we're going to have the derivative of natural log of n, which is 1 over n, the derivative of n, which is 1, and we end up with 0 over 1 there when n goes to infinity. And we take that limit, so we get e to the 0, and e to the 0 is 1. Now, once we get this 1, remember this is only part of the limit we were actually taking, so we want to go back and plug it in. So remember, we had the limit as n approaches infinity of the nth root of n quantity squared. So we've got that 1 squared, and then that's going to go right up here on top. So the limit as n approaches infinity of the nth root of n squared over 2 is going to equal 1 squared over 2, which is just 1/2. Now, what do we know about the 1/2? Well, going back to our rules, remember, if the L, the limit we came up with, is less than 1, then this thing is going to converge. If the L is greater than 1, then the thing is going to diverge. So 1/2 is definitely less than 1, so this series is going to converge. All right, so here's another example. We're looking at the series n goes from 1 to infinity of 2 to the n over n squared. I'm going to do the nth root test again. So when we take the nth root here, we're going to end up with the nth root of 2 to the n over n squared. Well, once again, we can split this up. Do the nth root at the top, the nth root at the bottom, and we're going to end up with 2 over the nth root of n squared. Now, we've already found the limit of this, and we can think about it the same exact way. We can pull the 2 out front, and we can think of that as 1 over the nth root of n squared, and just find the limit as n approaches infinity of the nth root of n squared. Remember, that was nothing more than 1 squared, so we end up with 2 over 1, and that's going to be 2. And what do we know? If the limit of this thing is a value that is greater than 1, then the series is going to diverge. So this series will diverge. All right, now remember when we first studied the integrals, we used a summation of rectangles to approximate the area under a curve. Now, this leads to us to the integral test. And what it says is if a sub n is a positive sequence and a sub n equals f of n, where f of n is a continuous function, continuous positive decreasing function, then the sigma, the series, sigma n equals n to infinity of a sub n, and the integral of capital N to infinity of f of x dx both converge or both diverge. Now, what this means is this. A sub n, remember, is a series. It's a sequence, or a sub n is a sequence. When we find the series, we're just adding them up. So what we're doing here with this, instead of the rectangle, we would simply have this value, and this value, and this value, and that value, and this value, and those would be the only things on here. We would actually not even have a function. A sub n is not a function. A sub n is a group of values. So this is all we're looking at when we're looking at a series. We're just looking at values that are going to occur at the integer values. 1, 2, 0, 1, 2, 3, 4. So we're not looking at any of that. We're just looking at these points. And then what are we doing? Well, we're adding them all up. Well, here's the thing. Compare that to our function. If we had that function that was just drawn up here, what do we know? If we're adding this value and this value and this value and this value and this value, as opposed to looking at the entire continuous function, what do we know? Well, here's the thing. This value right here, and this value right here, and this value right here, and this value right here is going to be a completely different animal than, and it's going to be a much greater, I mean, you're looking at area here. And when we actually calculate this, notice it's going to be larger than this value right here if we actually found the entire area. If we found that entire rectangle, it's going to be greater than 1. So if we were to find the integral under this, and the integral actually approaches a certain value, then of course the series of just this value and that value and that value and that value would approach a certain value too. Now that they're not going to be the same value, but they're either both going to converge or both going to diverge. So you can actually use a function defined by your a sub n and take its integral, and if that integral does not go to infinity, in other words, if it actually approaches a value, then that means that your series of a sub n will also converge. Now, obviously, it has to be continuous, it has to be positive, and it has to be decreasing. If it's increasing like this one you're probably looking at and saying, well, that makes absolutely no sense. And you're right, it doesn't. As this thing grows and grows and grows, the area is going to grow and grow and grow. It has to be a decreasing function, or there is no chance of this thing converging. So, does the sigma from n equals 1 to infinity of 1 over n to the square root of n converge? Well, let's see. We can do this with the integral test and just integrate it from 1 to infinity of 1 over x to the square root of x dx. Well, if we put those together, that's going to be x to the 3 halves. move it to the top, it's going to be -3/2, and we integrate. Of course, going off to infinity, that is an improper integral, so we're going to have to use a limit in the process. And when we do, we're going to take the antiderivative of the negative x to the -3/2, and we're going to get -2x to the -1/2 power. Integrated, evaluated from 1 to b. We plug that stuff in and let b go to infinity. So what's going to happen with this one right here? Well, this one's going to approach, if we do the square root of infinity, that's going to be a really big number. -2 divided by some big number is going to be 0, so that one's going to go to 0. So the limit's going to approach 2. Well, what does that mean? Well, that means that this integral approaches a value, which means that this thing right here, this series, is going to converge as well. Since the integral converges to the value of 2, the series must converge also, but not necessarily to 2. The integral does not find what the series approaches to. It just finds whether it approaches a value, a finite value, or not. All right, so this one's the one we've talked about for a little while, but we haven't been officially introduced. And it's called the p-series test, where we have a series that's made up of the a sub n element of 1 over n to the p power, where p is a constant. It's not changing. The n is changing. Remember, with our series, n starts at 1 and goes to infinity. It's a counter, but the p does not change. So we get 1 over 1 to the p power, 1 over 2 to the p power, 1 over 3 to the p power, and continue on forever. Now, it converges if p is greater than 1, and it diverges if p is less than or equal to 1. So if we had 1 over n, this series would diverge. If we have 1 over n to the 1.00001 power, this series will converge. So that's the big thing right there. You got the counter raised to a constant power, and if that constant power is greater than 1, it's going to converge. The series will converge. If it's less than or equal to 1, the series will diverge. Now, we could show this with the integral test, but we're actually not going to. All right, so the harmonic series, and it's just the series of 1 over n, it's going to diverge because the numbers do not get, they do get smaller, but they don't get smaller fast enough. It is a p series with p equals 1, which we know diverges. Now, because the p-series is so easy to evaluate, we commonly will use it as what we're going to compare to other series using the comparison tests. And we talked about the limit comparison test, but here it is. If we have a sub n is greater than 0 and b sub n is greater than 0 for all n greater than or equal to n, where n is a capital N is a positive integer, if the limit as n approaches infinity of a sub n over b sub n equals c, some constant, and c is between 0 and infinity, so it's positive, then both a sub n and b sub n converge or both diverge. So remember, this is a comparison test. B sub n is one that you're going to choose. And if you're going to be able to choose one, you're going to want to choose one that you can actually find whether it converges or diverges. So if you prove that this limit right here is some constant number, some positive constant, then you proved that what you've proven is that these are growing at the same rate. So that if B sub n converges, then A sub n is going to converge. And if B sub n diverges, then A sub n is going to diverge. So that's what you're actually looking at right there. Now, if the limit as n approaches infinity of A sub n over B sub n equals 0, then A sub n converges if you know that B sub n converges. Because what you've proven right here is A sub n is going to grow at a slower rate than B sub n. So if B sub n converges and A sub n grows slower, then it has to converge as well. And then the last one is if the limit as n approaches infinity of A sub n over B sub n equals infinity, then A sub n diverges if B sub n diverges. So what you've proven here, remember we've used this type of situation before to determine whether or not functions grew at the same rate. And that's what we're doing right here. And when we go to infinity, that means that the top is growing faster than the bottom. So if we know that B sub n diverges and A sub n grows faster than B sub n, then A sub n has to diverge as well. All right, so looking at this example right here, we've got 3/4, 5/9, 7/16, 9/25, and this comes into the nth term expression of the sigma notation from n equals 1 to infinity of 2n plus 1 over n plus 1 squared. Now, when n is large, the function is going to behave like 2n over n squared, or 2 over n. Now, 2 over n is always going to be greater than 1 over n. Now, what do we know about 1 over n? Well, 1 over n is a p-series, and a p-series that has a p-value of 1. So if 2 over n is greater than something that we know that it diverges, what do we know? Well, we know that that is going to diverge as well. But we've got to show the work, so let's go ahead and do it. So we're going to do the A sub n, this thing up here, and we're going to compare it to 1 over n. So of course we're going to keep change flip. So we've got 2n times n gives me 2n squared over n plus 1 quantity squared. When you simplify that stuff out, you're going to get this right here. When you take the limit as n approaches infinity, you're going to get 2. So what that means, remember, is that if this over this, the limit as n approaches infinity, is equal to a constant, that means they're growing at the same rate. And what did we say we knew about 1 over n? It's a p-series, p-value of exactly 1, therefore this thing's going to diverge. Well, if this thing diverges, and we've proven that they grow at the same rate, this one has to diverge as well. So since the 1 over n diverges, then the series, and when we say the series, we're talking about the series we're testing here, diverges as well. All right, what about this one? So we get 1 over 1 plus 1/3 plus 1/7 plus 1/15, and that ends up being the sigma notation from n equals 1 to infinity of 1 over 2 to the n minus 1. So when n is really large, the function is going to behave like 1 over 2n. Remember, that's negligible. We can kind of toss it out as n gets larger and larger and larger. It's going to have less of an effect on the denominator. So we can actually use that to compare it to. So when we do our limit, we got 1 over 2 to the n minus 1 over 1 over 2 to the n. Keep change flip. So we're going to end with 2 to the n over 2 to the n minus 1. And once again, as we go to infinity, that negative, that minus 1 right there is going to become negligible as these numbers get larger and larger and larger, so you're going to end up with 1. Now, what does that mean? Well, that means that the two functions, or the two series, this top one and this bottom one, grow at the same rate. Well, what do we know about 2 to the n, or 1 over 2 to the n? Well, that is a geometric series. What are we multiplying by each time? We're multiplying by 1/2. So when we multiply by 1/2, remember what do we know about a geometric series? If we're multiplying by, if our common ratio is a value that is less than 1, then the series is going to converge. So since 1 over 2 to the n converges, and we've proven with this limit, with the comparison test here, that they grow at the same rate, if 1 over 2n converges, then this original series is going to converge as well. All right, alternating series are series whose signs are going to change from term to term. In other words, one term will be a positive, the next term's negative, the next term's positive, etc. It's going to go back and forth. That's where the alternating series comes from. The signs of the term will alternate. Now, good news. If the absolute values of the terms approach 0, then an alternating series will always converge. That makes a test that is really, really, really easy, because 9 times out of 10, an alternating series test is going to look really complicated. It's going to have a -1 in parentheses to some n power, whether it be n or n plus 1 or n minus 1, but that's what's going to alternate the series. And when you take the absolute value, what happens? Well, you pull that part out. You don't have to worry about it. And then you have a much simpler series to look at, and if you can prove that it converges, then that alternating series converges as well. Well, let's look at an example here. So we've got the sigma notation n equals 1 to infinity of -1 to the n plus 1 power times 1 over n. This part right here is the alternating part. When n changes, this power is going to go from from an even to an odd to an even to an odd to an even to an odd. And what's going to happen? Well, when that power is even, this is going to be a positive function. When that number is odd, it's going to be a negative function. So that's where our negative comes in. The 1 over n doesn't matter. And all we have to do is take the absolute value and prove that the terms approach 0. We don't have to prove that the terms actually, or the series, the absolute value of the series actually converge. As long as the limit of the terms approach 0, then the alternating series is going to converge. So this is, if we take the limit of 1 over n, it does approach 0. Therefore, this alternating series right here will converge. Now, it is convergent, but it's not absolutely convergent, because what do we know? Well, remember, to be absolutely convergent, the absolute value of the function or of the series would have to be convergent as well. And what do we know about 1 over n? Well, it's the harmonic series, and it's not convergent. So this one is conditionally convergent. Now, since each term of a convergent alternating series moves the partial sum a little closer to the limit, we have this theorem, the alternating series estimation theorem. Now, for a convergent alternating series, the truncation error, in other words, the amount that you chop off if you start ignoring terms, is less than the first missing term and is the same sign as that term. So if we chop some terms off, we take that first term that we're ignoring, that we're getting rid of, and that term is going to be the value for that term. Sorry, the error for that term is going to be less than that term right there. So this is a good tool to remember because it's a lot easier than the Lagrange error bound. Now what this means, just to clarify, because it seems like I was kind of mixed up or kind of confusing there for a second, I want to make sure you understand. So we've got a sub 1, and it's alternating, so it'd be minus a sub 2 plus a sub 3 minus a sub 4 plus a sub 5 minus a sub 6 plus a sub 7. And let's say we want to be accurate, and we'll take 7 terms, and then we want to see how far we are off. So the unknown, the first one that we're going to chop off, is going to be minus a sub 8. And what this says, the truncation error, the error we're introducing to this thing from chopping off the rest of these terms, is less than the first missing term. So our error is going to be less than negative a sub 8, and the same sign as that term. So in other words, we're going to be less than the actual value of this thing by a value that's less than this thing right here. All right, now there is a flow chart on page 521 that might be helpful for deciding in what order to do which test. Mostly, guys, there's no way to get around it. Just practice, 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 and seeing what works, recognizing different types of tests that work for different types of series and things like that. It's just going to take practice to recognize what works. You can do summations on the TI-89 if you want to. I don't know that this works on 84. You can check it out and see, but you're not going to have to do anything like this. Most of these are going to be no calculator, just to be honest. All right, that's